right. Okay. Apologies for the brevity of the break. We would have liked to take a little bit more time for food and socializing, but we have a number of presentations to go, and I'm pretty confident in saying they're going to be great. So, really excited to introduce our next speaker. This is another case where the SIP advisor, Peter Cyber in Botany and Environmental Studies, he's hosting someone else on campus today who was able to join us for this event. But he sends his apologies and his good wishes, and so I get to introduce Eden. Eden Sisson. This is another case where I've known Eden from the Good Engineering seminar for a couple, 3 semesters here at least, and have known the whole time that that Eden is an awesome student. But I didn't quite see research until recently, and I think well, you're going to see it's pretty terrific work. One thing I want to mention about Eden's work that I'm also just really excited about is there's a through line in a couple of the projects this year. I'm thinking about Grace's work. We're kind of elevating the small organisms, and so we're going to see more about marine copepods today. So Eden, go ahead.
Yeah, so I'm Eden Sisson. I am the class of 2024, a botany major and English minor in the Good Engineering Center for the Environment, obviously. And my senior integrated project focuses on plankton adaptation in response to ocean warming and acidification conditions. So, as a little background, the 3 courses that I took during my undergraduate for Good Engineering included environmental anthropology, freshwater ecology, and organic chemistry. And these kind of exposed me to marine microorganisms and my fascination in them, in studying them and what implications they have for larger marine ecosystems. And then I also took a gap year after my sophomore year of college, and I spent a lot of my time living in the wilderness on these coastal deserts of Baja, Mexico. And I became really fascinated by these different coastal habitats and the organisms that I found there, and really started thinking about how I could relate my interests, my classes, to what I was experiencing there. So from here, my senior integrated project focused on a small crustacean, ubiquitous planktonic copepod called the Kershiotonsa, and these are about 0.5 millimeter to 1.5 millimeters in length, and they're important indicator species, like Grace mentioned, because they're so widespread and they're really sensitive to climatic changes such as temperature warming and ocean acidification. They're distributed globally and they're only found in coastal habitats, and they're really easy to culture in laboratory conditions, which is why they're used a lot. So working with this, I just wanted to mention a key concept with ocean warming, which is that with ectotherms such as copepods, with warming conditions, their metabolisms tend to speed up, and over generation to generation, they reach maturity faster, which means their mature size is smaller, and this has implications for different variables such as predator-prey dynamics, escape mechanisms, their ability to migrate vertically and throughout the water column, among other factors. And so, based on this is just one of the mechanisms in research right now, but my research and the research I did was located at University of Connecticut Avery Point Marine Campus. We're very excited to having license, and it was based on a 2021 publication within the same lab I was working in on the rapid but limited zooplankton adaptation to simultaneous warming and acidification conditions. So I was using the same lineages of a Kershiotonsa that I'm going to explain that I used in my research this summer, or last summer I should say, And it studied them over the course of 25 generations under 4 major laboratory conditions, including ambient temperature and ambient CO2 conditions, warming conditions, ocean acidification or high CO2 conditions, and then a combination of the both. Ambient being 18 degrees Celsius and 400 microatmospheres, and then high CO2 being 400 microatmospheres, and high temperature being 22 degrees Celsius. And what they found was over the course of these 25 generations, after an initial decrease in fitness, the copepods were able to make rapid but not complete recovery. And so to continue this experiment, we were looking at these same lineages of copepods kept in these conditions over the course of 150 generations or more. So as background, we use the same basis for the 2021 publication. As you know, global temperatures are warming. From the graph on the left, you can see in the past 140 years, as well as the past 1,000 years, you can see that more long-term change. And also CO2 concentrations are increasing. So our assumptions were based on maximum expected CO2 levels to be around 2,000 microatmospheres between 2,100 and 2,300, an increase of 31% atmospheric CO2 since 1750, an increase of 0.6 degrees Celsius over the past 100 years for global average surface temperature. And then we assumed an average surface water warming rate in the ocean of about 0.03 degrees per year. So these are the basis for the 2021 publication. So we use these same experimental conditions for consistency. So over the summer, as well as throughout my fall semester, I worked in the lab studying a variety of measurements within these copepods, including egg hatching rate, egg production rate, developmental time, sex ratios, and survival to maturity. And these measurements were used in accumulation to measure fitness of the copepods over time. And the results after 150 generations, very generally, we're still working with them. We're doing reciprocal transplants to get better results, which is when we return them to their original conditions. But the ocean warming and acidification group experienced an 18-degree increase in fitness since the 25 generation period. And then it was interesting that the other two treatment groups separately actually experienced a slight decrease, but mostly plateau after the 25 generations. So this was showing that they're continuing to recover, and the possibility of evolutionary rescue is a possibility, I guess. So thinking about this and the different relationships copepods might have in their ecosystems, I did a larger literature review for my senior integrated project looking at copepod fitness in the presence of ocean warming and acidification, a comparison between 3 marine habitats. And these habitats included mangroves, coral reef habitats, and then kind of looking at other coastal ecosystems and in general as well. So I want to go over a couple of them briefly, but there was a lot of mechanisms that I looked at. But yeah, some of the interesting ones, I guess. So mangrove habitats are very significant because of their high genetic diversity, their role in carbon sequestration, sediment control, nutrient organic matter cycling, flood mitigation, amongst other things. And so because these habitats are so important and complex, they have a ton of species that are interconnected in how they relate to one another. So here, this diagram kind of gives a little illustration of one of these relationships. So phytoplankton are very prevalent in the mangrove habitats, which thrive off of the detritus, so the decomposing organic matter coming from different organisms such as fish and birds, as well as the copepods themselves. And then the copepods are eating the phytoplankton, that's their main food source, and then feeding the planktivorous fish, which then circle around and produce more of that decomposing organic matter, which allows the actual mangrove plants to grow. So thinking about how copepods, where they are in this chain, and if they're to change in some ways in terms of size or abundance, their ecological changes, or like smaller like adaptations, how this would affect the food chain as a whole. And yeah, and then similarly with coral reef habitats, I did a lot of research on other kind of chains of events like that. So looking at copepods living in symbiosis with coral reefs, jellyfish, sea anemones, and other organisms, and then supplying these fish with food, which then promote algal growth and more nutrients. And coral reefs similarly house high biodiversity. They provide wave barriers to a lot of coastal habitats, as well as being homes to fish, and having a lot of symbiotic relationships like this. So thinking about these kind of dynamic relationships, I came up with conclusions that were kind of lack of conclusions, I think. I think my research was really interesting, and it exposed me to the immense genetic and phenotypic diversity of copepods, but also the complexity of ecosystems and how it's really hard to come up with conclusive or satisfying results from studying one like small microscopic species, while it might have very large cascading effects in these ecosystems. All the other species are changing as well with warming temperatures and acidification conditions. So there's tons of variables at play, including geography, climate, inter and interspecies diversity, predator-prey dynamics, and more. And so as you can see this cool little diagram, just all different copepods and how much they vary. And so I think that was my main takeaway from my literature review. And yeah, so not super satisfying, but interesting. And that's it. I wanted to acknowledge and thank Professor Peter Seiber, Lisa and Awaldo, the PhD students who I worked really close with at UConn, and I still do, Dr. Dom, the head of the lab, and then the whole Good Engineering team as well. So,
I think Skylar next on the list. Though I forgot to give you the heads up, if that sounds okay. So I get to introduce Skylar Cardell. I'm so. Let me just say, I just feel so lucky that somehow I ended up being the one who gets to work with him on this project. It is a fantastic project. Skylar is in the middle of it. You should know. He's in the middle of a 2-semester honors thesis in environmental studies, planning to finish up and graduate in December. And so this is a bit of a mid-term progress report, but he's already done so much, has so much to share. So I think we're getting a really great look at the research. It has been a blast to meet briefly and talk about evolutionary theory, metaphors in science. It's just absolutely wonderful. So Skylar is going to talk about vagrancy in birds. So.
Thank you, Dr. Turner. Hi everyone, my name is Skylar. I'm a student in the Good Engineering Center for the Environment, and today I'm going to be discussing my honors thesis in collaboration with my thesis advisor for the Department of Environmental Studies. And we looked at the role of vagrants on a changing planet. What vagrants are, we're going to get into in just a sec. But first, let me tell you about what I did this summer, should I say winter, because I was in the Antarctic during months of July and August, which are of course the austral winter months. I spent 5 weeks working and living on a 270-foot Antarctic research and supply vessel owned by the National Science Foundation, the Lawrence M. Gould. And I was there with a team of biologists from the City University of New York. We were looking at climate change and the changing abundance of seabirds and marine mammals around South Georgia in winter. I got to work with some of the coolest people. These were all experts in their field who were extremely willing to share their knowledge with 3 undergraduate students who were on board, including my personal hero, Dr. Richard Beat, whose work focuses heavily on this topic of vagrancy. And when you're down there for 5 weeks, you kind of become familiar with some of the more common or expected species one might find in one of the harshest marine environments on the planet. And that's going to be a lot of petrels, albatross, and of course, penguins. But then you also have some species which seemingly have no earthly business being there, including this Kerguelen petrel, which nests primarily 4,000 miles away on the remote Kerguelen Islands. Now in the 80s, when this survey was originally being conducted, Kerguelen petrels were an extremely infrequent occurrence around South Georgia. At the time, they just started nesting on nearby Duff Island, and they were thought maybe to possibly start breeding on South Georgia in the near future. And in 2012, scientists on the island actually found several pairs nesting along the inaccessible south shore of the island. And now, through our research, we believe them to be an established winter resident as well. We saw a lot of Kerguelen petrels. And this story of exploration leading to eventual colonization is one of vagrancy, right? What happens when birds show up way outside their normal geographic distributions? And we have a lot of different hypotheses for why this happens, some of which are better supported than others. But let's focus on this term vagrant for right now, and I use scare quotes intentionally because we have a lot of misconceptions about vagrants. And it's a word we use today to describe like a grifter living on the streets of New York or some other geographically mobile or otherwise itinerant person, usually with a negative context. And this really has a basis in this inherently nationalistic worldview that the everyday movements of people and animals are defined by the areas we draw for them. This is not something that's new. These beliefs date back to the poor laws of Tudor England, where vagrants and vagabonds were brandished with a red-hot iron V and forcibly removed back to their homelands, where they were condemned to live as slaves for their former communities. And now we see these beliefs manifest themselves in the form of anti-immigration laws, residency rights, anti-asylum measures, truancy laws. But when we apply these beliefs to the natural world, then we have to start doing all these mental backflips in order to account for the ultimately random movements of birds and animals. And we come up with these pseudoscientific theories on reverse migration and mirror image orientation. Basically assuming that a bird, which was supposed to be traveling in one direction, ends up traveling in the opposite direction and ends up somewhere completely different. And these views have been highly publicized, but they're based on a rather large assumption, which is that migration is static and linear. We look at the breeding and non-breeding ranges of this paleotropical migrant, the garden warbler, and it's very easy to assume that this bird is going to be found just within the colored areas predefined for it. And it might even be tempting to draw lines of best fit because line is the shortest distance between 2 points. But what this fails to take into account is that migration is the product of 2 things, distance and direction, neither of which are ever fixed values. And when we look at this eBird-generated abundance data, we can see different populations of garden warbler utilizing different geographic areas across different times of year at different rates. And that migration is actually this incomprehensibly complex series of everyday movements. And we know this. This is not something that's new. We know from one of the most foundational pieces of ornithological literature on orientation that yes, birds might orient themselves in the net direction in spring and fall, but they actually orient themselves in every direction, north, south, east, west. It's seldom, if ever, along these strictly north-south gradients. Which brings me to my third myth, which is that vagrants are just these passive victims, these mindless vessels of fat and feather that just get blown off course by prevailing winds. And we saw this happen last year when a couple dozen New World warblers showed up on the western shore of Great Britain. And birders and ornithologists there were very quick to assume that this was because of Hurricane Lee, which presumably came up through the Canadian Maritimes, picked up a bunch of these airborne migrant wood warblers, and then deposited them thousands of miles to the east over in Western Europe. And this is the same logic we apply to when European birds show up stateside. So every couple of years we have this European shorebird called the lapwing show up in some numbers in New England, and we just assume it's because of these strong nor'easterlies. But the thing is, these weather events happen every year, and seldom do they bring with them boatloads of New World warblers or European shorebirds. And this is confounded by recent evidence which suggests that some birds are actually able to fly clean through these storm systems without altering the degree, right? This is a radio-tagged numeral which flew through the upper right quadrant of Hurricane Irene in 2011 and came through the other side apparently unscathed. And this is not to say that weather has a completely negligible effect on bird movements. We know that it does. Following tropical storms that come up through the Gulf, we occasionally get a smattering of inland records up to a couple of dozen miles of this highly pelagic seabird called the sooty tern. And this is because of a stress-induced hormone called corticosterone. But this hormonal imbalance is not enough to account for displacement that occurs on hundreds, if not thousands, of miles. Something else is going on. And we know now, thanks to a recent outpouring of ornithological research dedicated to the subject, that vagrants actually are the primary drivers behind species range migration and species range migration. These are the expanding fringes of these exponentially growing populations, usually involving highly fit offspring. Not these sick or defective birds, but these exceptionally physiologically fit hatchier birds that are undergoing exploratory behavior. And in a way, these findings are not remarkable because this is the same logic we apply to other areas of the animal kingdom. So when a mountain lion shows up in coastal Georgia, we assume it's because the population in Florida must be thriving, and then we begin conversations about how to curb or otherwise mitigate that population. But for some reason, with birds, whether it's because vagrancy involves longer distances or larger geographic scales, we assume that something else is going on. And these findings have been popularized by several well-known examples, including this great blackhawk, which showed up in coastal Maine, and a stellar seagull, which is still kicking around eastern Canada. And this brings me to my argument, which is that there is a desperate need for a new framework to understand vagrancy. And this starts with the terminology we use, because vagrant itself is an imperfect term. Dr. Beat has suggested we use the term Argonaut instead, in reference to the Greek band of mythological explorers. Historically, vagrants have existed as sort of this background noise in these larger data sets. Now, in order for these data sets to remain relevant, we must incorporate vagrant data into them, right? When we're presented with the possibility that these ancient and historical migratory routes will become inextricably severed due to climate change or habitat degradation, we cannot assume that these carefully evolved life histories will become hopelessly unraveled. We know that these birds are already evolving. Now we ourselves must adapt in order to recognize them as the cognizant and capable actors they are on a changing planet. And I'd like to thank my home islands of Nantucket, Tuckernuck, and Muskeget, my thesis advisor, Dr. Derek Turner, my research mentor, Dr. Richard Beat, and everybody else I can. So, thank you. That's it.
Sarah, I'm so sorry. Did I skip Sarah? Sarah. Oh my gosh. Sarah, come on up. I feel bad. And Professor Thompson, I'm totally I'm like so excited. Would you like to present your name So, Professor Thompson, take it away.
So I'm very happy to be up here to introduce Sarah. I was fortunate enough to be Sarah's pre-major advisor, so I have known Sarah in my advising now for 4 years, and it's been a really great 4 years, I will say. I think one thing to keep in mind when you start hearing about what she has to say is just how well she's prepared for this. So, the area of green energy is really interesting to a lot of people, but there's a lot of different ways to involve that, right? You can do the engineering, you can do the kind of policy side of things, you could do more of the kind of siting kind of stuff. She has the engineering background, she's got the kind of siting kind of background, she's done the social science stuff, and you're going to see a lot of that in what she has to present. So very impressed, so thank you.
Thank you. Okay, my name is Sarah Hall. I'm a genomics major with a geoscience minor, and for my SIP, I completed an honors thesis, which is titled GIS-based multi-criteria decision analysis for marine energy site selection. And so with the emerging climate crisis, there's also an urgent need for climate action. And many countries around the world, including the US, has established ambitious climate or renewable energy goals. And in order to meet these, we need to look at alternative sources of energy. One of these is the ocean, which has a very high power potential. And there are a lot of different technologies that can be used in the ocean. One of these is a wave energy converter, which is pictured here. There are many different devices. There's also offshore wind, there's tidal turbines, and riverine is also included in ocean energy. But as we're doing this renewable energy transition, we also need to make sure that it's both sustainable and just. And because the marine energy industry is in such a new stage, there's the ability to incorporate sustainable practices into all parts of projects. And so during a project's timeline, site selection is a critical time during the project. And this is when we can incorporate these environmental justice frameworks into the project. Currently, most energy siting projects only consider technical factors. So if you're looking at an offshore wind turbine, you're going to look at the wind speeds and the wind direction because this directly influences how much power is going to be produced. But by doing so, you're disregarding all of the environmental impacts and the social impacts that these projects have. And so there are now new methods that are emerging that allow for the incorporation of both social data and environmental data to make more equitable siting decisions. One of the primary tools for this is a software called Geographic Information Systems, or GIS, and this enables the easy visualization of geospatial data. Multi-criteria decision analysis, or MCDA, is a way of weighting criteria and analyzing it to create an overlapping analysis. And so by combining these two things, you can create a comprehensive site selection analysis. This method has been used extensively for onshore renewable energy projects, but it has yet to be applied to many marine energy projects. So for my thesis, I chose to use GIS-based MCDA methods and apply it to 2 case study locations for 2 different marine energy devices. And so the first location is the island of Puerto Rico and then the islands of Hawaii. And I'm considering 2 different marine renewable energy devices. The first is a coastal structure integrated wave energy converter. or a CSA WEC, which is pictured up here in the top right. And this is a more newer niche device that is a combination of a wave energy converter that has been integrated into a coastal protective structure. And so these are often rock seawalls that you'll see off in the shoreline, which are designed to provide coastal protection from erosion, but also from storm surges during hurricanes. And so these have a dual benefit of providing both coastal protection, but also clean energy. And then in Hawaii, I'm looking at a hybrid wind wave solar system, which is also a fairly new technology that combines both offshore wind turbines, floating solar, and then wave energy converters. And for this project, I specifically wanted to highlight how including social justice data impacts our siting decisions. This on the left is my GIS methods, which is complex and not really the point of what I did. So if you want to know more, you can come and talk to me about it or read my paper. But the two analyses that I conducted for each site, the first was a technical site suitability analysis. This included all technical data, so energy resource data, proximity to power lines, proximity to ports and cities. And then the second was a social justice site suitability analysis, which included all the technical data, but also included social justice data. And so I'm going to walk through the methods with this first case study, which is Puerto Rico. The first step is criteria selection. So there are 6 criteria included. This starts with the wave resource. And then I have 2 social justice criteria, which have been pulled from a data set called the Justice 40 data set, which is funded by the White House and is pushing for more equitable decisions throughout the federal government. So the first identifies energy disadvantaged communities. This looks at energy cost, reliability of energy. And then the second is identifies climate change disadvantaged communities. So this looks at communities that will be impacted by sea level rise or have high amounts of people in workforces that will be impacted by climate change. And then the last 3 criteria are port proximity, city proximity, and power line proximity. These are really important for also the cost of a project and logistics for installation and maintenance. And so to visualize what these criteria look like in GIS, this is the wave power. Yellow is low wave power. Purple is high wave power. And you can see, especially in Puerto Rico, there's a high wave energy resource along the North Shore. This is a map showing the cities, ports, and electric transmission lines. And then this is an example of one of the Justice 40 data sets. This is energy disadvantaged communities. And so these are all combined using the GIS methods, and then based on the previously shown weightings, they are combined into this final suitability map. And so this is the social justice suitability map, which includes the Justice 40 data sets. And blue is low suitability, red is high suitability. I completed these same methods to produce the technical map just without the Justice 40 data set. So my final figure is this, and the top is the social justice site suitability map, and the bottom is the technical site suitability map. And they're pretty different, which is my most important finding, is that by adding social justice data, you're going to get different siting decisions. More specifically, if you look along the southern coast on the social justice site suitability map, that is ranked as highly suitable versus with the technical site suitability, that's not a place that you'd look to put a project. And now going on to Hawaii. These are the criteria selected. These are different because we're now looking at the hybrid wind wave solar project. So the wave resource, the solar resource, and the wind resource were all ranked highest because for a hybrid system, it's really important that you have a high correlation of all 3 energy resources. And then for this project, I looked at just a general Justice 40 data set that identifies disadvantaged communities. This looks at poverty level, it looks at workforce, it looks at education. And then I looked at port proximity and power line proximity again. So using the same methods, I created this final figure that on the top you see social justice site suitability, and then on the bottom is the technical site suitability. blue shows low suitability and red is high suitability. And so both maps are pretty similar. The northern shore of the islands are pretty suitable sites for a hybrid system. But when you add in social justice site suitability or site criteria, you actually get a reduction in the overall number of suitable sites, which is different than what happened in Puerto Rico. And this is most likely due to the way that I weighted the Justice 40 data set. In this analysis, I ranked the locations that were closer to a Justice 40 community as lower, so that we're making sure to provide a buffer around mainly Native Hawaiian populations that rely heavily on the marine space for their economic and also cultural activities. And so this is shown again in this. The main differences between the two is that for Puerto Rico, when you add the social justice criteria, you actually get an expansion in the number of suitable sites, where in Hawaii you get a reduction. But for both maps, with these methods, you find suitable sites, which is really important for using GIS and trying to get this into the industry. But it also demonstrates the importance of including social justice criteria when you're completing these siting decisions. So those are my main conclusions. Also, one of the biggest takeaways from this is that both case studies demonstrate that GIS-based MCA methods can be used for a wide range of locations and energy devices. And so I'm continuing to work with the National Renewable Energy Lab to develop this and hopefully apply to future projects, both internally with the company and also for external commercial companies, to hopefully make sure that our continuing site selection is done in a way that's equitable. And these are my acknowledgements, especially thank you to Doug Thompson for all of his help in this and everyone in the Goodwin Hearing Center.
Thank you, Sarah. Also, I apologize again for getting things out of order. Total mess up on my part. But such impressive work, so important. Hannah, maybe now you want to come on up. I'm also just thrilled to be able to introduce our next speaker, Hannah Grinnell. One of my own favorite philosophical topics to think about is sense of place and how people and communities connect with places. And Hannah and I, it's just been a wonderful time this semester meeting, reading some wonderful stuff and thinking and talking about sense of place from week to week, while Hannah has been working out her own angle on things and her own ideas about sense of place, and also going to talk to people, as we'll see in just a second. So Hannah,
Hi everyone, my name is Hannah. I'm an environmental studies major and an English minor, and my SIP is on community agriculture as place-based resilience. So I wanted to start with a little bit of a mini exercise for everyone. I was really hoping you could all just take a few moments and think about a place that you love, a place that's special to you in some way, meaningful to you in some way. Maybe it's a place you've been to many times or maybe once and it had a really big impact on you. But maybe for a moment, just think about that place. Imagine yourself there. And ask yourself questions like, why is this place important to you? How do you feel when you're there? How do you feel towards this place? These are some of the questions I was thinking about when initially beginning to dive into this project, and kind of informed a lot of my thinking. So I've always had an interest in combining the humanities and the environment, which is why I wanted to be in the center, because I wanted to take an interdisciplinary approach to my education at Con. But I also credit my personal connection to home and the place that I'm from as being really formative in my interest in this topic. That's me on the Great Marsh, which is in northeastern Massachusetts, where I'm from. And I spent 3 summers working out on the salt marsh, and it's such a special place to me. And I started reflecting a lot at the end of my time working there on the role that that place has played in my life, how it's informed the way that I care about the environment and also just the place that I'm from. And then an ironic connection is my FYS, my first year was Conceptions of Home and Place, which could kind of be an alternative title for this presentation. But I came to Con in the spring, not the fall, so this was the only FYS offered, so I had no choice but to take it, but now it's kind of full circle, because I'm here talking about place. So just a little bit of background, I took 3 courses to inform this project: Literatures of Utopia, Environmental Philosophy, and Disasters. And then over the summer, I worked for the Food Project, which is a nonprofit based in the greater Boston area, focused on empowering marginalized communities through building more equitable and sustainable food systems. And so for the whole summer, I basically just worked on a farm, which was what I wanted to do. I wanted to gain that very immersive and hands-on experience in farming and agriculture to kind of start thinking about some of these things. And so it was a summer of a lot of hard work, but also connecting with that place. I worked at their Lincoln farm, which is right outside of Boston, and I hadn't spent a lot of time there before the summer, but I spent obviously the whole summer there and got really familiar with it. And looking at these photos now, kind of seeing the land represented, the food we were growing, and also the people that I got to work with, I kind of see those 3 things intersecting in a way that made me think more about kind of what place means. And led me to this bigger question: in what ways can place be used as a tool to foster more connected and resilient communities? And I say place with a capital letter because I think the way that I have grown to think about place in the context of my project is it's not just kind of the static landscape and the background and the environments that we live in. It's something very dynamic that possesses a lot of agency in the ways that it impacts us as people and our communities and how we live our lives. And so that's kind of the way that I'm using it in this project. So the methods that I took, Derek and I did a lot of reading this semester. We read Trace by Lort Savoy, The Pine Island Paradox by Kathleen Moore, The Unsettling of America by Wendell Berry, and then Wisdom Sits in Places by Keith Bassow. And I'm gonna try to keep this super brief. These were really amazing texts and I got so much out of them, and I wish I could delve into all of them right now, but I can't do that. But I just pulled some quotes that I feel like kind of speak to what I am drawing from them for my own personal project. And so in Wisdom Sits in Places, Keith Bassow talks about how sense of place can be seen as a commonplace experience, as an ordinary way of engaging one's surroundings and finding them significant. And from this, I'm kind of trying to speak to the idea that sense of place is something interactive. It's something we engage with on a daily basis. He quotes someone in this text as well, saying sense of place is something we do. And so I'm kind of trying to emphasize that it's something like tangible and active, not just the backdrop to our lives. And then in the Pine Island Paradox, Kathleen B. Moore has so many amazing things she says, but this is from her chapter on what it means to love a place, where she's talking about how to love a place is to care for it, to keep it healthy, to attend to its needs as if they were my own, because they are my own. Responsibility grows from love. It is the natural shape of caring. And a foundation of her work on place is that loving places is a lot like loving people. When we love people, we want to do what's best for them. We want to maintain their well-being, make sure they're safe, make sure they're cared for. And from this kind of grows this sense of moral responsibility that she talks a lot about in her writing, and also kind of refers to this ethic of care that we then have towards places. And so that's kind of what I'm pulling from her work. And then The Unsettling of America by Wendell Berry, which kind of formed a really perfect culminating text for this project, because as much as I'm talking about place, I'm also specifically zeroing in on the relationship between farming and place. And he's a very notable voice in agricultural writing. And he talks about good work, which in the context of this, he is referring to farming as like the enactment of connections. And I think this is a really beautiful way of describing the ways that farming is a lot about the way everything is interdependently connected within a community between the people, the land, the plants. It's not kind of this arduous drudgery work. It's something that's really alive and is about stimulating those connections. And so, like Derek said, another piece of my project that I really wanted to explore was actually having interpersonal conversations with people and going to farms in the local area and talking to people who are engaging in this work on a day-to-day basis. And so I was able to actually go to 2 farms. I went to Stone Acres, which is in Stonington, if anyone's been there. And I spoke with John Morris, who's actually the CEO of Stone Acres. And then I went to Huntsbrook, which is in Quaker Hill, and spoke with Rob, or Digga, as everyone calls him. And I had some really amazing conversations with both of them. This is kind of a fun visual I put together of my attempt to kind of map this story of place. And so there is a third point. I'm hoping to go to Fresh New London next week. I wasn't able to do that before today. But to kind of complete this triangle of collecting narratives and stories of people who are engaging with sense of place very actively within their lives. And so I wanted to pull also a quote from both of those conversations. I talked with John. It was really interesting because he is coming into this from a finance and business background. He is from New York City and actually came to Stone Acres 4 years ago as the CEO and had no prior farming experience, which he told me. But he did say this interesting quote during our conversation talking about that he thinks the reason why people get into farming is because of the place, which I thought was really interesting because as someone who doesn't have direct farming experience, he still could recognize the connections between those two things and speak to it still, which is why I kind of pulled that one out. And then I had a really great conversation with Digga. I loved talking to him. He was super cool. If you can ever go to Huntsbrook, you should, because he's just a really cool guy. He started the farm when he was 23 and has kind of been growing it ever since. And now they have a CSA and they have a market there as well. And he's kind of like a farmer through and through. This is what he's done for most of his life. And when I was talking to him, he had a really interesting perspective on place because not only was he speaking to the natural beauty of this area, he also was emphasizing the importance of those interpersonal connections being really intertwined in place. And at one point was talking about how he runs the farm as if, like, when you're there, you're part of the family, and that's the love that this place really needs in order to flourish. And I liked that he kind of recognized that there's so much care and energy that has to be put into places to kind of make them come alive in a sense. It's that enactment of connections that I talked about earlier is very relevant here, and it was cool to kind of see him talk about it just in different words. And so admittedly, I am still writing my paper for this project. So the outcomes are kind of still coming together and they're not fully articulated. Things are really overflowing in my brain right now. So I have right now, though, this kind of visual diagram that Derek and I were talking about that I really loved the idea of kind of putting these 3 works into conversation with each other. Also, I want to say Trace by Lord Savoy will be also discussed. I just couldn't fit her in this for the moment, but it's also a great book. But from Bassau, pulling this kind of sense of place as being interactive, more contributing ecological ethics of care, and then very kind of speaking to the ways that health, wholeness, and connection are really intersecting when it comes to farming. And for me, for my paper, exploring how farming facilitates this kind of placefulness through these things. How farming is cultivating connections and how connections are really the foundation for health and for wholeness, and that's how we're going to be hypothetically building more resilient communities for the future and forming models of care, how we care about places on an individual level and also on a community level, and promoting this kind of ethical sense of responsibility that we have for the local environments that we live in every single day. And so, yeah, and then I forgot I threw this in there, but this is a quote by Elizabeth Berry, which I thought was really also beautiful. I couldn't help myself. Connection is health, which I think thinking about place and farming and the connections that arise from those two things, health is kind of, as he says it, this like thread between the two. And since my project is really on understanding place and resilient communities, I think that this is just kind of like a resonating quote I wanted to end with today. So I wanted to give a thank you to Jen, Kelly, Derek, my advisor, Professor Neely, the farm team, family friends, my friend Sherry, and also to places that I love and that have formed me as a person.
So, yeah.
I have the extreme pleasure of introducing David today. I'm sorry your advisor can't make it. I made a deal with David. I'm going to give the talk. No, I'm just kidding.
I prefer that.
Yeah, I really just want to say David's a really special soul. Any of you have met him, just to be in a room with him or to be around him, you can sense how extraordinary special he is. When he came to talk about potentially applying to the center, he actually had the same project. He's been very, very consistent, which is very rare, as you might have noticed tonight. But also, it's not just your integrity and your passion, David, that is so special. But as you'll see, he can really tell a story and make you feel like you too are a brilliant chemist. So take it away.
After such a wonderful intro, I'm going to say I think it's going to be all downhill from here, but we're going to enjoy the ride together. That's the point. So, as Jen wonderfully said, my name is David Mulaba. I'm a senior here in the center. I'm a biochem and botany double major and ES minor. And the title of my project and what we're going to be talking about today is thinking about developing efficient methods of synthesizing a natural product called fermentosity. So for now, that's word salad, but hopefully we'll describe what that means a little bit later. And before doing that, I just want to give a bit of background about myself. When I first came to Con, I was kind of your stereotypical standard biochem student. I was only interested in biochemistry. Of course, I had some interest in medicine and pharmacology as a career plan, but even then, I was only approaching those topics from the perspective of chemistry. So I was always asking myself, who are the great chemists? So if you think about like the 20th century, for anyone familiar, we're looking at like Corey and Woodward, and especially more recently, some scientists like Sharpless and Bertozzi, other great folks, do a lot of great chemistry. So I was always asking myself, what would it take to be like a great chemist? That was my central question. However, as a first year here at Con, we also have general requirements as a first year course. So as one requirement I wanted to get out of the way was something we have called the CC requirement, or the Con course requirement, meant to be interdisciplinary. So I was looking at the course catalog and I saw this 101 botany class. I believe it was plants and climate change. And it's like, okay, gardening back west isn't too bad. Might as well, decide to take it. And for any of the folks who've known her, it was taught by the now retired Professor Hine. She was so wonderful, completely changed my outlook. I fell in love with the department, and I really haven't looked back. I always tell folks I feel bad. I basically, since that class, have stuck around in the botany department like an invasive species. That being said, one part of that class I really enjoyed was we got our own 1 meter by 1 meter plots in the greenhouse. That's what we were looking at up here. And over the course of the semester, I was actually surprised I was able to successfully grow some zinnias. And because I'm kind of a killjoy, I was thinking like, okay, these zinnias have great flowers, but I wonder what chemistry is inside them. So it turns out that within zinnias are a whole family of compounds known as the flavonoids, which is the image that we see over here. And well, as you might imagine, a lot of complicated ring systems, a lot of functional groups. But the reason why we care about these guys is because they have antioxidant properties, and also kind of more recently, they were discovered to be pretty effective against fighting the docking proteins of COVID. So kind of just a more relevant example of that. But in any event, again, I was kind of asking myself, wow, I think a plant like that could produce these compounds that have such inherent complexity and they do it like that, all without even thinking. And so it really made me question my initial question of when I asked myself, who is like the best chemist out there? If you would ask me that question today, I kind of just, I'm gonna be so dramatic, but I'd say, look outside, and all of that greenery out there, it can do amazing chemistry without even thinking, just like that. So with that kind of realization, I decided to apply to the Engineering Center, and the rest is history. Speaking of that history, over the course of those next few semesters, I was trying to think more about what I wanted my senior project to be about. Of course, I really enjoyed organic chemistry as the class. I was really fascinated with organic synthesis theory. So that's kind of substantiating this first bullet point over here. I was also, fortunately enough, through the center, was able to take a few more supporting courses, one of which being Botany 225, which is our plant systematics course here. Really fantastic course that gave me the tools and terminology that is required to start studying botany at a systematic level. And I use such positive adjectives, not just because Professor Jones is joining us tonight, but it's okay. That being said, I also took another botany class known as the Ethnobotany of Southern New England, which is taught by Professor Lizarralde. And that's a really great class too, especially in my journey, because it helped me look at relationships that people have with plants that extend beyond just like scientific study. So particularly involving a lot of indigenous perspectives on the people-plant relationship. So again, great course. And also, I had to bring some chemistry back in, so I took analytical chemistry, and that I would also say is a fantastic course because it really made me respect procedure and all of the equipment that we have in the lab, which is pretty fundamental if you're going to be doing a science thesis. And then lastly, as you might imagine, writing out synthesis schemes on paper or doing organic chemistry homework is a bit different than actually doing it in the lab. So I wanted to kind of try my hand at that. So when I was trying to put all of these things together, I landed at the topic of natural products chemistry, which is the main focus of my thesis work. And thankfully, unlike a lot of terms in science, it's kind of self-explanatory, where it is the chemistry of products or compounds that are made naturally in nature. And again, fortunately for me, as a part of my junior summer, I was able to work in Dr. Vasquez's lab as a part of our Summer Science Institute research program here at Con. And again, even continuing that great good luck for me, Dr. Vasquez's lab actually focuses on the synthesis of natural products. So one product that he looks at in his lab is something called guanic acid A. It's a really interesting compound that comes from a fungus. Another compound that he looks at is something called frondosine D. And that is a compound that is produced by this sea sponge over here that is naturally occurring in the South Pacific. And while, don't get me wrong, it may need a bit of a makeover to look like its friend up there, it is what is on the inside, as my mom would say, that counts. And what is on the inside, in this case, is a whole family of compounds known as the frondosins. Frondosins are of interest to Dr. Vasca, but also just the scientific community more broadly, because they are antioxidant, antiviral, also tumor suppressant. And specifically, it is frondosine A and frondosine D that have been currently identified to be the most potent in terms of those medicinal properties. So along those lines, this summer, Dr. Vasca kind of tasked me with trying to work towards synthesizing frondosine D, which is the molecule that we have pictured here. And it's since this summer that I've really built on that work, and that's turned into an honors thesis that I've continued over this past year. So I don't want to put everyone to sleep. So this is just like a bit of an overview of some important organic chemistry concepts I think that is nice to have as a baseline. So at the end of the day, right, when we think about biotic systems or just the chemistry of the natural world, everything is carbon-based. For the most part, everything is carbon-based. So if you're starting to think about what makes a good synthesis reaction, I would say one criteria is that it can make new carbon-carbon bonds. If you can do that, fantastic. Okay, great. Well, what about sometimes we don't just want to make new carbon bonds that can freely rotate. We also want to make carbon bonds that produce ring systems. Problem is, as you might imagine, because now we're forcing things into a ring that introduces rigidity, and carbon molecules don't always like to do that. So if your reaction can do that, even better. Moving forward, as you might imagine, not all shapes are created equal. Turns out in chemistry, based on kind of bonding angles and just the natural arrangement of the way carbons like to position themselves, If you have a 5-membered ring and a 6-membered ring, that's the most stable. So if your reaction can make a non-5 carbon or a non-6-membered ring, even better. And what's great about the work that Dr. Abasca does is we actually have a reaction that does just all of that, all 3 of those criteria. And that is called the Claisen rearrangement. And so that is something that we're looking over here. In this case, what that does is when you have an oxygen with a vinyl system, which is that red double bond up there, and an allyl system, that's this blue double bond here, when you have this whole setup, introduce it to a little bit of heat, you'll naturally get this rearrangement, and you'll get a new positioning of things. Okay, cool, well, why does that matter? Well, what we do in the lab is set up systems like this where we have an alcohol, this OH, we have this vinyl system here, this red double bond. We can turn these blue triple bonds into our allyl systems, going back to the blue that we saw above. And then again, as this final arrow says over here, expose that setup to a little bit of heat, you'll get your rearrangement, and you get 7-membered rings. So pretty powerful and pretty cool. And before moving on into any more synthesis schemes, I just kind of want to take a bit of a detour and show us what the day in the life of the lab looks like. So as you might imagine, when it comes to organic synthesis, water can be the enemy. So we really always want to eliminate any sources of hydration. So in that case, this is also why we will flame dry everything typically when we start our reaction. We also like to keep things under inert atmosphere, hence the balloons up top that are filled with nitrogen gas. Also, if you ever want to keep things cold, we use solid blocks of CO2 or dry ice. And then also, if you wanted to think about monitoring a reaction, we have something called TLC plates that we can use UV lights to check, okay, did this new dot form, did it not form? Questions along those lines. And moving forward, here's some of the fancy equipment that we have over in the lab at Hale. On the left, here's our rotovap. And when it comes to the rotovap, we carry out our reactions in solvent. Solvent is just a fancy way of saying it's a liquid that helps us facilitate reactions as they're coming. It also helps regulate heat control and stuff like that, whatever. But the main idea is that you need solvent to run a reaction. At the end of the day, you're not going to be isolating solvent. So you need somewhere to get rid of it. That's what the rotovap does. It will spin, it will rotate, and evaporate the solvent as it goes. Okay? You got rid of your solvent, but what about that crude mixture? It's a mix of good stuff and bad stuff, stuff that you want, stuff that you don't want. That's where our handy isolated biotage comes into play. What this helps us do is we can put our crude mixture into it. It will run a solvent system through these columns and essentially allow us to isolate the good stuff, the stuff that we want, versus the bad stuff, the stuff we can leave behind. After that, once you have, in theory, your good stuff, you can send it over to the NMR machine, and if it's having a good day that day, it will actually give you a spectra that tells you whether or not did I actually make what I wanted to make. And also, I just want to throw up here up top, just in case, when I said microwave earlier, I wasn't talking about the one you make popcorn in, so when we throw reactions in there, it's this fancy machine up here. And for anyone who can kind of see, I just wanted to throw in this bottom spectrum line at the bottom just to say that, as anyone who works with lab equipment knows, there's a direct relationship between how cool and useful it is and the tendency for it to break. So in that case, as we go from left to right, we have an increasing likelihood of getting ahead. So that's the idea. Cool. So now kind of going into the more, not theoretical, but just the overall scheme or schematic portion of the discussion. We talked about the reactions that I actually carried out. When we think about frondose and D, there's 4 main ring systems. So I like to think about the overall synthesis pathway as having 4 main milestones. Okay, so up top, you have the first ring system. Then after that, we can get to our second ring, which, believe it or not, only takes place in 1 reaction. And then after that, we get to our tricyclic intermediate, and then finally down to our tetracyclic product. Thankfully for us, over the past few weeks and past few months, getting to our tricyclic intermediate, that DCB product, is actually pretty well established. You can take a commercially available ring D, do something called a Baylis-Hillman reaction, it gets you to rings D and C. And after that point, what we have to ask ourselves, it's great we got to 2 rings, but we need some more sources of carbons to actually get anywhere else, to continue building out the structure. So that's why we have this second line over here, where what we're trying to do is install a tether or an arm that we can attach onto that bicyclic, that DC ring system. So then, once we have that tether attached, we can do the Claisen rearrangement and we can get to our tricyclic product. That's the whole goal of that second row. And the actual attachment in the Claisen rearrangement is what we're showing in this third line over here. The problem with this is that even though it works great, once you get to this tricyclic intermediate, there's not a lot of options to move forward because you don't have a lot of functional groups at these positions to do your final tetracyclic transformation, which is why the focus of my research was thinking about, okay, how can we make something a bit more useful before we go from this pre-cyclized to this then cyclized product. So along those lines, the first thing we tried was something called the catechol Charkiewicz approach, was again, take your pre-cyclized product at the top, extend that tether. Instead of just having it with that initial 4-carbon chain that ended with that initial triple bond, attach more carbons, then cyclize that, so you have a tether that's there at the right position that you can use later on in the synthesis. In theory, once you have that triple bond there, you can use something called a zipper reaction, just like zipping up a coat. It will move the triple bond all the way to the terminal position. You can reduce it, and then do something called the Heck reaction, which will end up with your fused 4th ring system. It seemed to work at first, until I sat down and looked at the data some more, and it turned out it didn't work, and it was kind of devastating. So I remember this was the day that I went to my advisor, Dr. Timo Vasco, and I told him, you know, Timo, I feel like really bad. I don't know if I want to keep doing this project. And he went into his office and he took out the signed document thesis form that I signed to basically agree to work with him. And he said, David, look at the form you just signed. It said you work with me for a year, not a few months. So get back to work. So along those lines, we got back to work. And then what we ended up doing was not completely throwing out the approach that we had before. So again, the catechol Charkiewicz approach was essentially just add a new tether. In this case, instead of having a new triple bond tether, we just have, if you can see up there, the TBSO group. It's what that allows us to do is try and introduce a different functional group, so that if it were able to get cyclized, we can then use that TBSO to hopefully get closer towards making that tetracyclic product. Problem is, it turned out that we weren't able to actually get to this pre-cyclized form, but when we tried to do that cyclization to get to the tricyclic product, that did not end up working out. But that's okay, because then we had one more approach, and this is something called the hydrazone approach, which is like, okay, it's February 1st, we're running out of options and running out of time. So throw out everything I just said about regioselectivity and the benefits of having a tether. Let's try and work with that tricyclic product. And in that case, we took that, we added on something called hydrazine. In that case, we were able to do a bit more manipulations to try and get an alkylated tether at the right position. Once it's there, you can then again do the Heck reactions and get to that fused form. Surprisingly, we've done all of this, and as of last week, I've done this long enough to know I cannot say that it worked, but we have yet to acquire evidence to say that it did not work. So, on that note, folks, I just want to thank everyone in the center. Of course, thank Dr. Timo Vasco, my fellow lab mates. As you can probably tell, working with me can be a time. So in that sense, to be a part of Research Share Con, to be part of the Guggenheim Center, it's been an honor. So I just want to say thank you for that. Of course, I just want to thank the Hale Career Center for all their funding. And although I think it has ruined my ability to enjoy watching SpongeBob SquarePants, I have to thank the city of Frondosa, that sea sponge, because without that sea sponge, I wouldn't be here today. So on that note, folks, thanks for listening.
I'll do the intro while they're doing the setup here. So I'm again fortunate that I have known Nona ever since she first, actually before she first got to Connecticut College. I've been her advisor throughout the entire process. If I remember correctly, our first ever meeting was, it was during the COVID years. It was via Zoom, and I believe you're sitting on like the porch of an old farmhouse, right? And, so it's kind of interesting because where she ended up is far away from the inland Midwest, right? So she ended up being very interested in the marine environment. She did a study abroad at Williams Mystic, and as you're going to see, she's now looking far offshore from her original beginning. So.
I'm Winona, an ES major, anthropology minor. Thank you, Judge, for that amazing introduction. Yeah, I'm from Ohio, and I'm studying the ocean. So that's a little weird. But the title of my SIP, which is an independent study that I did with Doug, is Fisherman Engagement in Offshore Wind in Europe and the United States. So a bit about me before I talk about my research. The summer of my sophomore year, after my sophomore year, I interned at Maine Green Sun, which is run by a Con alum. It's a solar company, and that sort of began my interest in renewable energies. In the spring of my junior year, I studied away at the Williams Mystic program for coastal and ocean studies, where my policy professor introduced me to the complicated issue of offshore wind in the East Coast. My center internship was a double internship that I did this past summer at The Ohio State University, where I studied climate knowledge and the past geological history of India. And this multifaceted work gave me great experience studying humans and nature, which is a theme throughout life and my presentation. Some classes that helped prepare me for this, U.S. Environmental Politics and Policies with Professor Torres, American Maritime History, which I took at the Williams Mystic program with Professor Zepeda, and Sustainable Food Systems with Professor Black. So some background of my project. As climate change progresses due to anthropogenic carbon emissions, countries across the world are turning to renewable energies. Offshore wind specifically is gaining a lot of support with federal governments. It has a lower carbon footprint, as we know, than fossil fuels, but not everybody is on board. Commercial fishermen, artisanal fishermen as well, are pushing back against offshore wind because it overlaps with traditional fishing grounds, limits normal operations, and might harm local ecosystems important for fishing. Getting fishermen on board with offshore wind will be critical for its successful expansion. And studies show that that can be done through direct engagement, including fishermen in planning processes. This brings me to my guiding questions. How have European countries and the US engaged or have not engaged fishermen in offshore wind? And what does this mean for addressing resistance to offshore wind? So I'll explain this a bit more. While there are many countries that are expanding offshore wind across the US, I wanted to compare what was happening in the US with what's happening in Europe. I first chose Denmark because Denmark was the first country to implement offshore wind in 1991. And then I chose the rest of the countries based on information that I was able to find quickly. These countries, I wanted to look at countries within the EU to understand how the European Union has an impact on offshore wind. So I picked 6 countries: Denmark, France, Germany, Norway, Spain, and Sweden. And these countries represent variation within how Europe is developing offshore wind. With Denmark, who was the first to start, to France and Spain, who are just now getting involved. And I compared the research that I did on these countries with the US. So that research is looking at permitting processes and case studies. So federal governments across the world typically have jurisdiction over the waters near their coasts. And this gives them authority to auction off areas for offshore wind. And in order for a developer to be considered, for that job, they go through what's called a permitting process, where they submit forms, plans to the regulatory agencies that have jurisdiction over within the federal government. This is a very lengthy process and can take years to go through. And I wanted to know how these processes involved fishermen. So I looked at the permitting processes within each of those 6 countries and the US. And this meant I was scouring government web pages, trying to make sense of bad translations for months. Additionally, I researched stories of fishermen protesting offshore wind in these European countries and the US. And I wanted to know what their reactions to offshore wind was and what changes they would like to see happening. And this involved looking at news articles, at essays, at sociology and anthropology papers on local fishermen and fishers associations. To formulate my conclusions, I integrated what I learned from the permitting processes and the stories of fishermen to understand how fishermen are engaged in offshore wind development and how to make that engagement better to reduce overall resistance to renewable energy. What I learned about the permitting process in Europe, I created this graph. It doesn't look like much, but it took me hours. I identified 6 types of engagement, and I have divided these into direct forms of engagement and indirect forms of engagement. So direct would be where governments or developers are specifically communicating with fishermen, and indirect where developers and governments are making choices to do with fishermen but not directly involving them. Within Europe, I found a high variation between countries and how their permitting processes engage fishermen. So Denmark, for example, used 5 of the 6 identified types of engagement, both direct and indirect, while France did not show any types of engagement. Additionally, most of the kinds of engagement I saw within these 6 studied European countries were indirect. What I learned from fishermen within these countries was that their main issue was that governments and developers did not communicate or include or consultate them in any forms of the planning. Within the United States, there was very little engagement from the permitting process itself. 0 forms, in fact. However, the 2 cases that I looked at, one was South Fork Wind, which is off of Long Island, and Vineyard Wind, which is off of Martha's Vineyard, I'm pretty sure, and both are in construction phases. They're not quite commissioned yet. Both of those 2 cases, there were lots of examples of engagement from the developer themselves. That included direct and indirect, which is pretty cool. However, most of the issues expressed by fishermen within the US was that there was a lack of consultation and research for choosing sites for offshore wind, which connects back to Sarah's presentation, which is super cool. Yeah, there was a lack of inclusion overall within site choosing. So some conclusions. Based on my findings from the 6 studied European countries, I would recommend that European countries implement more direct types of engagement within the permitting process to foster more communication and inclusion from developers and fishermen, and that the US include fishermen when choosing sites to minimize future conflicts. Thank you to Doug, my SIP advisor, my internship advisors, Rocky, Jill, Atri, Good Veneering, Jen and Kelly, you're amazing. Derek, Michelle, French family visit.
Thanks, Nona. I want to take a second to say a special thanks to Professor Doug Thompson, former director of the Good Veneering Center, who has done a ton of work this year with students, and we've seen 2 of those projects, but we're not done. So, Doug, if you want to come on back up and come on.
So I have the pleasure of introducing Emma and her project. Emma did, I think, a good job preparing for our site. And she was really interested in doing a project on environmental economics. And as you probably know, I am not an environmental economics person. So unfortunately, what had happened is the person she had planned to work with unexpectedly left the college. So Emma kind of contacted me in a bit of a panic and said, what do I do? So I pitched a couple of different ideas to her, and based on the course she'd taken with me, eventually convinced her to, instead of doing, a literature-based things, to get her hands a little dirty. Actually, her hands got a lot dirtier, shoes, her pants, everything else. And I think she's done a great job.
So, thank you, Doug. As my introduction said, I was preparing to do a project in the economics department with an environmental economist on the potential of increasing battery storage power for solar panels. And so then I contacted Doug and was like, well, that's not going to work. And he was like, well, solar panels are being installed on campus. And I was like, solar panels, sure. So we ended up on the title of An Investigation of Wetlands, Connecticut College as a Case Study, which I'm very happy that it ended up this way. It's been great. So to kind of inform my SIP originally, I decided to take 3 classes, climate, society, hydrology, and ecological agriculture. Unbeknownst to me, I'd be doing the project that I am now, and hydrology with Professor Thompson and ecological agriculture would inform a lot of the methods and processes that I went through during my project that I ended up with today. I also was a summer intern at a state authority. I'm from upstate New York, and I was a state environmental quality review intern, which we looked a lot at permitting. We looked a lot at the wetlands in New York and how to deal with changing infrastructure and permitting process. So it kind of all came together in reality. So over the summer, Professor Thompson emailed me and was like, well, the college got a grant to put in a very large solar array. And so a couple months ago, starting my project, beginning of the spring, we did a site assessment. We went on a walk with some of the solar company representatives and contractors and engineers. And we realized that there was a large overgrowth of phragmites, which Carrie mentioned in her project is very indicative of wetlands. And there also happened to be a lot of standing water, a lot of very saturated and wet soil conditions just based off of visible observation. So we were kind of in this state where we're like, well, the site in general seemed kind of poorly engineered. There was a couple of culverts and catch basins down kind of the bottom sloping part of the site. And we weren't sure, is it because of the engineering of the site that there are these wetlands? Is it even a wetlands in scientific classification? So we had a lot of questions going into it. So just for a bit of background before I jump into it. So a wetland soil up here on the left, if you see that middle portion, that really gray zone of soil, that is very indicative of poorly drained, unoxygenated soil, which is indicative of a wetland soil. The right image is actually a picture that I took in the field of one of the soil cores that I took. So as I'll discuss, that is not what we look at when we look for qualities of wetland soils. So kind of bringing it all together and going into the project, we looked at this very long 267-page PDF from the National Cooperative Soil Survey that had already analyzed the entirety of campus and the site where we were going to be looking at the soil conditions, and they already classified it. So within this long PDF, they have different acronyms and different names that they give to soil classifications. It's very random. So the site where we were working and the whole of Connecticut College was classified as PDB, which is Paxton and Montauk soil. It has nothing to do with the actual properties of the soil itself. It's just a random name that was applied to it. So we ended up with the research question: does the soil testing and analysis done through this project match the conclusion that was made in 1983 through the National Cooperative Soil Survey? Furthermore, does the soil analysis done in this project align with the state of Connecticut's definition of wetland soils? And the state of Connecticut defines wetland soils as poorly drained to very poorly drained, which from a scientific standpoint sometimes is very hard to contextualize and set a list of criteria to study for. So basically what we were looking at is back to this picture of, okay, we're going in trying to see if we see any indications of this gray, unoxygenated, poorly drained soil. So for the field methods, like Doug said, we got really dirty. I had my rain pants on from rowing. I had just gotten off the water from 6 a.m. practice, and at one point Doug just had to say, like, you're gonna get dirty, there's going to be dirt all over you, and I was like, okay. So we took these two pieces of equipment over on the left. One is on the left-hand side is an auger, which is a more, which is a bigger piece of equipment to collect a larger sample. The smaller one on the right is a hand soil core that we ended up doing the small samples from the first two red dots on the left and using the soil auger for the most right-hand red dot. So we took smaller samples, field samples at the first two red dots, and then took a large soil sample from the right-handmost dot to take back to the lab to do analysis. So from the field results, this is where you get dirty. You basically pick up a piece of soil out of your soil core from your sample, and you follow this flow chart, and it asks you a bunch of questions. What's the texture of the soil? Can you form a ribbon, which is when you take the soil chunk and you rub it in your hand and try to see if it forms like a ribbon. So yes, we were very dirty. So the field samples, we got all the way down to 60 centimeters, which isn't too deep, but gave us a good indication of what we were looking at. And we did color matching in the field using this little book where you pick up a piece of the soil and you hold it up to the light, and there's this little translucent patch, and then there's a color, and you just try to match which color the soil is to these swatches in a book, kind of like paint swatches. And so then I also went through this flow chart to do a field analysis of the texture of the soil. So this is what we came up with. Definitely a variety of sand, silt, and clay. The field sample too definitely had a lot more clay in it, or so I thought in the field. When we got back to the lab with all the samples, we went through a much more extensive routine to do some more concrete analysis. So our lab methods, represented in pictures, on the left is this machine where you fill up a 1,000 milliliter graduated cylinder, or equal to a liter of water, and you put 40 grams of your dry soil sample in. And then you stick it under, and that little piece that goes like this. And you turn it on, and it whirs around, and I kind of felt like a Dairy Queen worker making a milkshake or something. And unbeknownst to Professor Thompson, the first time he left me alone in the lab, I turned it on too fast, and the whole sample went flying out the top all over me, and I had to redo it. You didn't know that. So after you mix everything up, you put a top on it, you mix it back and forth to get everything in suspension, you put it down, start a timer, very nervously wait for 40 seconds, and then you drop in the middle piece of equipment, which is hydrometer. So at the end of 40 seconds, there are going to be all of the sand particles in your sample that have settled at the bottom, because sand, per the diagram on the bottom here, is larger than your silt and your clay, so they're going to have a faster settling velocity. So when you drop your hydrometer in, you read your first measurement, that's going to tell you the percentage of sand in your sample. Then I had to wait 2 hours, hung out in the lab, and then at the end of 2 hours, I dropped the hydrometer back into my graduated cylinder. So at this point, all the silt had settled because it's going to have the second highest velocity, settling velocity. And so then you take that reading. So then all that's left in your sample is your clay, because it is the smallest and lightest of the particles. So that is going to have the slowest settling velocity. So then using the calculations on the right-hand side of the screen, you can actually calculate the percentage of sand, clay, and silt in your samples using those methods. So some lengthy lab results from the actual hydrometer method that I did on the right, using the sample that I took using the larger auger that got all the way down to 93 centimeters, which is pretty good. Before we hit some rocks, we physically couldn't go any farther. Doug made me try. I was putting my entire weight on it. It wasn't happening. So what I found was that the field samples that I had taken and the field analysis I had done looks a little different to what was actually done in the lab analysis. There was a lot more silt. You can see the sample from 60 to 80 centimeters is a little bit more sandy than the rest. However, what was more important to me was the fact that the Montauk and the Paxton series are labeled as fine sandy loams. So I was seeing a lot more silt in these samples than I was seeing sand. I also did some other calculations and tests. There's a image on the top right, which has little X's on the data point that I found to be true for those samples. So we looked at things like, the texture more. We looked at the size of the actual PEDs, which are the dried particles of soil. We looked at the shape. I found that they were like angular blocky little PEDs, which are really just means they're like irregular shapes and kind of look like a triangle or a square or something in the middle of that. So after looking at all this, I was like, okay, so we're seeing some discrepancies in the samples that I took in the lab in the series that was analyzed by the National Cooperative Soil Survey. However, I was also looking at the lab methods that I had done on the top right-hand corner, and I was like, well, those are kind of in line with what the properties of the Paxton and the Montauk soil series are saying. So my conclusions, I came to four main ones: that the texture in the soil sample taken at the field does not precisely match up with the soil texture of the Paxton and Montauk series, but it also didn't match up with the lab analysis that I had done. There are a few soil series with a silt loam texture, which is what I got in the lab analysis, and those are just random names. There's one that's like a Narragansett series that is a silt loam texture. However, the color match tests done in both the field and in the lab are consistent with the colors of the soil series with a silt loam texture. So both the soil series with a silt loam texture and the Paxton and Montauk series are defined as well-drained soils. So they're not going to be defined as very poorly drained soils, which are going to be indicative of a wetland soils. And even though when we're taking all this data into account, the best soil series description I found still was the Paxton and the Montauk series, even with the discrepancies somewhat in texture. It could be related more to the Narragansett soil series in terms of texture, but there were differences in the color analysis. And so putting all the data together holistically, which I could go into a lot more, but for time's sake, overall the soil does not seem to be presenting as purely wetland soil, but there still are these standing bodies of waters, these overgrowth of phragmites, which are indicative. So the samples that Doug and I took in the field are not indicative of wetland soil, and they kind of match up with other soil series, but they also match up with the Paxton and the Montauk series. And so some slight discrepancies, but this is what I came up with. So thank you, like all of us, to Doug, to amazing Professor Derek Turner, to Jen and Kelly for being the life and light of the center, and to Professor Michelle Leary for a wonderful semester last semester, and all my family.
Thanks, Emma. And Corinne and Ted. Thanks to everyone. I know it's a long evening, but this last talk is gonna be awesome. So I'll
I'll introduce the last talk. This is not a green energy talk, believe it or not, even though the last ones were. It actually is interested in both architectural studies and environmental studies. And she did a really great internship, I think, that really informed her interest over the summer in New York City, working in a kind of green space in the city. And she wanted to kind of take that to think about what would like the perfect design be of a really resilient kind of green space in the New York City area, and I was happy to help her with that project.
Thanks, Steve. Hello, everyone. My name is Corinne Benedidis, and I'll be presenting on the project Not So Concrete Jungles, Designing Urban Parks for Flood Resilient Cities. As Doug said, I'm an architectural studies and environmental studies double major, so even before coming to Con, I've always been really interested in the intersection between architecture and cities and the environment and seeing how they can better coexist. And through my time in Goodwin-Nearing, that interest has sort of evolved into looking at how landscape architecture and urban parks can be used as tools to make cities more sustainable and resilient to climate change. In terms of preparing for my senior integrated project, I interned this past summer at the Prospect Park Alliance in Brooklyn, New York, as an ecological restoration intern. So my work was all about invasive plant management in an urban park, and I would walk around to different sites throughout the park and record the native versus non-native plant species presence to just get a sense of general forest health. And 3 courses that I took to prepare for my project were a wide variety of courses. So one was an environmental studies course, hydrology. Another was an architecture course, urban renewal in America, New London. And one was an English course, literatures of utopia. So I was just trying to get a very interdisciplinary perspective on the environment, cities, society, and just looking at how all of these can come together and intersect. So moving into my senior integrated project, the problem that I identified was that cities are full of impermeable surfaces like sidewalks, roads, building rooftops. And the issue is that when there's rain and the rain falls onto these surfaces, it is immediately converted into runoff and it travels over the surface instead of permeating into the ground. So this just causes severe flooding issues. This can be a problem in a lot of older cities because many of these have what's called a combined sewer system where wastewater and stormwater are transported in the same pipe system. So as you can imagine, when there's a lot of input from a big like storm event, these sewage systems can very easily overflow. Another issue is the pollution of water bodies. So as runoff is traveling over these surfaces, it picks up a lot of contaminants and pollutants like just litter, car fuel, different chemicals, and it carries these contaminants into the water body that the water eventually ends up in. So this leads to a lot of water pollution issues. So I wanted to research how parks can reduce urban flooding. The solution that I came up with, or that I researched, was green infrastructure, which can look like a variety of different projects, but the main goal of green infrastructure is to capture and retain runoff in place until it can be reintegrated into the natural water cycle. So green infrastructure is able to reduce both the volume of runoff and the speed at which that water is traveling, which can alleviate flooding conditions and also reduce sewage overflow and pollution of water bodies. And green infrastructure elements are starting to be employed in landscape architecture all throughout the world, which is very exciting. So for my project, I conducted a literature review of some of the green infrastructure features out there. I also looked at a bunch of case studies of flood-resilient urban parks, both in the US and around the world. And I culminate with a proposal for a design for a flood-resilient urban park at a site in Queens, New York that currently experiences heavy flooding. So one of the first green infrastructure features I looked at were rain gardens, which are depressions in the landscape that are filled with a layer of gravel, growing medium like soil or sand, and vegetation. And the idea is that unlike the impermeable surfaces that are all throughout cities, rain gardens provide a permeable catchment that can capture this water and allow it to filter through the ground and recharge groundwater. And rain gardens can also be useful in removing pollutants from stormwater runoff because they are bioretention systems. So the plants and microorganisms in the soil can, when they absorb the water, they can kind of absorb those contaminants sometimes through nutrient uptake. This is just an example of a linear rain garden at one of my case study parks in Shanghai. You can see how the rain garden is running alongside the road, so water traveling over the road can just be filtered right into the rain garden. Another feature I looked at was retention ponds or retention basins, which collect and retain stormwater for longer periods of time. And an emphasis here is placed on the fact that this water is directly reintegrated into the natural hydrologic cycle. So instead of being transported away from the pond through like an artificial watercourse system. The water either directly evaporates from the pond or permeates into the ground or is just directly released into a nearby water body. So this is one example from another one of my case studies in Bangkok. And just some additional features I looked at. One was permeable pavement, which is exactly what it sounds like. Unlike normal pavement, which doesn't really allow water to filter through, permeable pavement is designed in a way that water can filter through its many layers and eventually make its way into the ground. And permeable pavement can also sometimes remove certain contaminants from the water as well. Another feature is just native plants and forests. Having heavy, like dense planting is a great way of slowing water and kind of just acting as a barrier so it's not moving as quickly. And then trees obviously just absorb large amounts of water, so just having native forests is a great way to reduce flooding as well. And finally, I looked at the manipulation of topography as a tool. So one example is in this image here I have of another one of my case studies. You can see how the topography has been manipulated so that there are depressions in the landscape that end up being retention basins, and then more elevated mounds that they put like pathways on so you can still navigate the park. So this is just a way of playing around with topography in order to direct where the water is going and make sure it ends up in a space that is like more convenient in a way that allows you to still interact with the park. So moving into my own design, I chose a site called Willets Point in Queens, New York. This is a former industrial site that has a long history of heavy contamination. So it was a like dumping ground for an ash removal company. It also had lots of junkyards and auto body shops. So it's just experienced heavy contamination. It's also a former salt marsh, so it's located in between Flushing Bay and Flushing Creek. The site has a very low elevation but a high water table, so that coupled with the lack of like sewage infrastructure on the site means that it's kind of perpetually flooded, and is also considered to be a 100-year floodplain by FEMA. So all of the blue there is the areas that would be flooded during a 100-year flood. So I thought that Willets Point would be kind of the perfect place to implement an urban park using green infrastructure. The green infrastructure would lessen severe flooding on the site, and the plants on the site would help to remove contamination by phytoremediation. So that's where these plants absorb water, absorb these contaminants, and then emit them through transpiration. And having a park here would also just provide additional green space for the community. So here's a zoomed out image of my site. There's supposed to be a highlighted section, but in this southeast corner, that small corner where the roads intersect is the specific site that I chose for my park. So the idea is that the park would serve as like a two-way buffer system. So if there was storm surge coming from Flushing Creek, the park would be able to intercept that water and prevent a lot of that from going further inland into the site. And on the other hand, if there was a lot of rain and the water is traveling through Willets Point, making its way back into the creek, the park would be able to take that water and remove contaminants before it makes its way back into the water cycle. So this is just zoomed in of my site plan. The part on the eastern side that like abuts the wetlands there has very highly modified topography. So those like concentric ovals that you see represent mounds, and then the two like single circles represent retention ponds. So this is what I was talking about with the manipulated topography. Water would be forced to funnel in between these mounds and into the retention ponds, where it can be held for longer periods of time. This space just in the middle, like the flat space, is just a lawn, but the idea is that it would be a floodable lawn. So if there was really high flooding and the retention ponds overflowed, they can overflow into the
into the lawn, which would serve as like an emergency retention space. And I was really trying to think about how the park could be used at different levels of flooding. So I didn't show the pathways on this drawing, but they would be made of permeable pavement and they would also interact with the mounds. So like I was saying, if there was a huge storm event and the lawn was flooded, you'd still be able to interact and navigate through the park by interacting with that elevated topography. And then just that rectangle there, that small rectangle represents a linear rain garden that would be there to collect any additional water and decontaminate it before it makes its way back into the system. This is just a concept sketch that I made early on. So yeah, Willetts Point is on this side, the wetlands and creek are on the other side. So the whole site has sort of an overall downward slope, so that water is just sort of ushered away from Willetts Point and back into the creek. This is a 3D rendering of my park design, so you can get a better sense of the topography and the retention ponds. I also tried to place an emphasis on a lot of dense planting on the side of the park that abuts the wetlands. So again, just having dense planting there means that it'll serve as a barrier to protect both sides as the water is moving its way through. I also had to think a lot about the tree species that I would include in this park. So in all of like the lower areas that would be flooded much more frequently, I chose species like sweet gum and swamp white oak that actually prefer wetter soils. And then for the more higher elevated areas, I chose species like red maple and hackberry that can tolerate both wet and dry conditions. And this is just an additional elevation view showing the topographic changes. Yeah, that's everything. Thank you so much to Professor Doug Thompson for advising me, to my internship advisor, Howard Goldstein, and the whole Goodwin Yearing team, Jen, Kelly, Professor Turner, and Professor Neely. Thank you so much.
So, I'm just so thrilled with all the work that everyone's done. Thanks. Maybe a round of applause for the seniors on the Thanks to all for joining us. Thanks again to all the advisors who worked with everyone, and have a good night. Enjoy the evening.